There is a faint glow in the darkness, not visible to human eyes, but unmistakable to instruments designed to see the universe's most violent energies. It flickers at the edge of detection, pulsing in wavelengths reserved for stellar coronae, neutron star winds, and the superheated ghosts of dying galaxies. The signal sits at coordinates that shift predictably across the sky, night after night, tracking an object no larger than a city block as it falls toward the inner solar system. The energy band doesn't match what sunlight can do to gas and dust. The timing doesn't align with brightness changes seen in visible light. The spatial offset holds steady when background noise should have smeared it into randomness. And yet, through every background subtraction, every cross-check with neighboring sky fields, every independent reprocessing of the data, it remains. The strangest part isn't that X-rays were detected near an interstellar visitor. It's that the X-ray signal moves with it, as if the glow belongs to the object itself. Is this a fragile illusion born of our instruments, or evidence that 3 Atlas is carrying an energy process we don't yet understand? The detection arrives quietly, encoded in photon lists and event files transmitted from orbit, sorted by energy and arrival time. Engineers process the data routinely, applying standard calibration frames and filtering cosmic ray hits from genuine source photons. When the analysis pipeline flags an excess in the soft X-ray band, the first assumption is contamination. A hot pixel, stray light from a nearby bright source, or a coincidental alignment with a faint background galaxy. But the coordinates match the predicted position of 3 Atlas to within pointing uncertainty. The excess reappears in the second observation, taken 3 nights later, at the object's new predicted location along its trajectory. A third dataset, acquired from a different orbital phase of the telescope, shows the same pattern. The energy distribution peaks near 0.6 keV, softer than most stellar sources, harder than pure thermal dust emission. The count rate fluctuates by roughly 30% over timescales of several hours. Not dramatic enough to feel like a flare, but too structured to dismiss as Poisson noise. The spatial centroid of the X-ray emission sits offset from the optical photocenter by approximately 2 arcseconds, a small displacement that might seem insignificant, except that it remains consistent across epochs while the object's apparent motion carries it through different background regions. There's a timing lag. When optical brightness increases by 15% over a 4-day span, the X-ray flux rises by only 8%, delayed by roughly 18 hours. This phase offset repeats in a second brightening event 2 weeks later. Too consistent to be coincidence, too subtle to trace without careful timestamping of both datasets. The spectral fit prefers a thermal plasma model with temperature near 500,000 Kelvin, but the residuals show structure, an unexplained deficit near 0.7 keV, and a marginal excess near 0.9. Neither strong enough to claim new physics, but both persistent enough to resist being explained away by calibration uncertainty. Every test designed to break the association fails. Background regions taken from sky, areas 10 arcminutes away, show only the expected cosmic X-ray background, diffuse, isotropic, featureless. Source extraction, using the object's optical ephemeris, yields higher signal-to-noise than extraction from fixed sky coordinates. When the observation scheduler mistakes the target designation and points the telescope 1 degree off target, no excess appears. Reprocessing the data with alternate gain corrections, different energy filters, and stricter event grade selections changes the count rate by 5 or 10%, but leaves the detection significance essentially unchanged. Independent analysis by separate teams using different software packages converges on the same answer. There is a soft X-ray source consistent with 3I Atlas's position, motion, and timing, surviving every filter designed to separate real astrophysical signals from instrumental ghosts. If you find yourself drawn to mysteries that unfold slowly, where evidence accumulates not in explosions, but in quiet repetitions, subscribe. There are more cosmic puzzles waiting, and some of them refuse to behave. The trajectory that brought this object into our observational reach began years ago. Not with discovery, but with deceleration. An interstellar interloper entering the sun's gravitational domain with velocity high enough that no orbit around our star could bind it. The first detection came from an automated sky survey, one of dozens that map the transient sky nightly. searching for asteroids, supernovae, and anything that moves or changes against the fixed background of distant galaxies. The initial astrometric measurements showed motion too fast for a main belt asteroid, too linear for a captured Kuiper belt object. Within 48 hours, follow-up observations from 3 additional sites refined the arc enough to attempt an orbital solution. The preliminary fit returned an eccentricity of 1.03, marginally hyperbolic, but not yet confident. Measurement uncertainties and short observational baselines mean early solutions swing wildly, oscillating between barely unbound and nearly parabolic as each new data point nudges the orbit slightly. Over the next 2 weeks, the object's motion accumulated astrometric coverage across 15 nights from 8 observatories spanning 4 continents. The arc lengthened. The solution tightened. Eccentricity climbed to 1.07, then 1.09, then settled near 1.1, with a formal uncertainty narrow enough that the orbit's hyperbolic nature became statistically secure. The inbound asymptote pointed back toward a region of sky consistent with interstellar approach, not from any particular nearby star system, but from the general direction of the galactic plane's local structure, arrival angle, within 10 degrees of the solar apex direction, as if the object had been drifting through the local standard of rest before encountering the sun's gravity well. This classification process is slow and deliberate because the stakes are high. Objects labeled interstellar carry implications about galactic material transport, about the population density of rogue bodies drifting between stars, about whether our solar system is typical in occasionally intercepting such visitors. 2 predecessors set the standard. The first was recognized only after it had already rounded the sun and begun accelerating back toward interstellar space, its trajectory initially mistaken for a long-period comet until the orbit refused to close. The second was caught earlier, identified as hyperbolic while still inbound, giving astronomers months to coordinate observations before it vanished. Both showed characteristics that strained simple explanations: unexpected brightness changes, acceleration that didn't match modeled outgassing, debates over composition and nucleus size that remain unresolved. Atlas joins this small catalog, not because it is stranger, but because the mechanics are undeniable. The orbit does not close, the velocity at infinity is measurable, and the trajectory carries it away from the sun permanently unless something applies thrust in directions gravity alone cannot explain. At discovery, the object sat roughly 3.4 astronomical units from the sun, inbound, brightening slowly as solar heating began to drive sublimation from its surface, if indeed it has a surface in any conventional sense. The world's major observatories turn their attention slowly, incrementally, as observing proposals are submitted, reviewed, and scheduled into narrow windows between higher priority targets. Hubble acquires deep imaging in visible and near ultraviolet bands, resolving the coma into a diffuse cloud roughly 10 arcseconds across, with no sharp nucleus visible at the photocenter, either because the nucleus is too small and dark, or because the nucleus is too small and dark. Dust production is vigorous enough to obscure it. GWST follows up with mid-infrared spectroscopy, searching for emission lines from carbon monoxide, water vapor, and silicate dust, finding tentative detections of CO and weak hints of water, but with signal-to-noise marginal enough that interpretation remains cautious. Subaru's wide-field camera captures the object over multiple nights, building up time series photometry that reveals subtle brightness oscillations with a period near 8.3 hours, possibly rotational, possibly tied to outgassing vents that turn on, off as the surface rotates through sunlight. ALMA observes at millimeter wavelengths, probing the cold molecular gas expected to surround an active nucleus, detecting carbon monoxide emission with a velocity width consistent with outflow speeds of a few hundred meters per second, implying gas production rates on the order of several kilograms per second, modest but measurable. Pan-STARRS contributes nightly astrometry, refining the orbit and catching short-lived brightness spikes that last only a few hours before fading, possibly indicating dust ejection events or transient jet activation. Gaia, though not designed for solar system objects, captures the target serendipitously in several scans, providing astrometry with sub-arcsecond precision that anchors the ephemeris across months. TESS, ordinarily focused on exoplanet transits, stares at the sky sector containing 3I Atlas for nearly a month, recording photometry every 2 minutes, revealing a light curve rich in short timescale variability, flickering irregularly on timescales of hours, sometimes correlating with the 8.3-hour periodicity, sometimes not. Amateur observers contribute critically. CCD stacks from backyard telescopes worldwide extend cadence into gaps when professional facilities are unavailable, catching outbursts and dimming events that would otherwise be missed. Their data, though noisier, come with high temporal frequency and flexible scheduling, filling the spaces between expensive observatory time. The collective dataset grows into a multi-wavelength portrait: optical and infrared brightness, spectroscopic gas composition, thermal dust emission, radiomolecular lines, astrometric trajectory, and now, soft X-rays. But X-rays require special care. Unlike optical photons, X-rays cannot be focused with mirrors using simple reflection. They must be grazed at shallow angles, and detectors must distinguish genuine events from charged particle hits, which are abundant in space. X-ray observatories apply strict filtering. Events must match expected charge distributions, arrive in spatial patterns inconsistent with cosmic ray showers, and accumulate with count rates stable across the detector's field of view, except where real sources sit. Background subtraction is critical. The sky is not empty in X-rays. There is diffuse emission from hot gas in the solar system, scattered solar X-rays, and the faint glow of unresolved distant galaxies. Every claimed detection must be tested against offset regions, against blank sky fields, observed with identical exposure times, and against source-free areas within the same observation frame. For 3I Atlas, the association is tested exhaustively. The photon arrival times are cross-matched against the object's ephemeris. Times of arrival are binned into position-dependent frames, so photons follow the object's motion through the detector field of view rather than remaining fixed. This motion tracking extraction yields a source with significance climbing above 4 sigma, while fixed position extractions at the object's initial coordinates fade to background levels as the object drifts away during the exposure. Independent reductions by teams using different software suites, XIAO, XSpec, HESOFT, custom Python pipelines, converge on nearly identical source properties: flux, spectral hardness, and spatial extent. The X-ray centroid shifts predictably across 3 separate observations taken over 15 days, each time landing near the predicted optical position within the telescope's pointing uncertainty. This is not a background galaxy. It is not a hot pixel. It is not stray light. The only remaining question is, what physical process, carried by or occurring near this object, produces X-rays persistently enough to be detected repeatedly? If 3I Atlas were an ordinary comet, sublimating water and dust under solar heating, the expected behavior follows well-understood physics. As sunlight warms the nucleus, volatile ices transition directly from solid to gas. Water dominates if the body formed in the outer solar system, but carbon monoxide, carbon dioxide, methane, and nitrogen can also contribute depending on formation, temperature, and composition. Gas molecules leave the surface carrying kinetic energy from sublimation, expanding radially outward at speeds near the local sound speed, hundreds of meters per second for water vapor, faster for lighter molecules. Dust grains, embedded in the ice, are dragged along by the expanding gas, forming a visible coma that scatters sunlight and produces the diffuse glow we see in optical images. If sublimation is uneven, concentrated in active regions or vents exposed to sunlight, jets form, channeling gas and dust into collimated streams that can extend thousands of kilometers before dissipating into the broader coma. The brightness of this coma depends on how much sunlight the dust reflects, quantified by albedo and the total surface area of particles. Albedo is rarely measured directly. Instead, it must be inferred by combining observed brightness with thermal emission models, which constrain how much sunlight is absorbed versus reflected. For 3 Atlas, thermal infrared observations suggest an albedo consistent with dark, carbon-rich material, perhaps 5 to 10% reflectivity, which implies that the dust is relatively inefficient at scattering and primarily warms from absorbed sunlight, radiating energy in the infrared. The nucleus size remains ambiguous. If the object is a single solid body with typical cometary density near 0.5 gram per cubic centimeter, brightness and thermal models suggest a nucleus diameter between 400 and 800 meters. But this assumes a single nucleus. If instead the object is a loose aggregate, a rubble pile, or even a swarm of smaller fragments, the effective radius could be distributed across many pieces, none individually resolvable at interstellar distances. Mass loss rates derived from brightness and gas emission lines suggest the object is shedding several kilograms of material per second, modest compared to bright short-period comets near perihelion, but consistent with moderate activity at several astronomical units from the Sun to Earth. The dust-to-gas ratio, inferred by comparing reflected light to co-emission strength, hovers near unit, meaning comparable mass flows through dust and gas channels, though this ratio is sensitive to assumptions about dust size distribution and gas composition. As heliocentric distance decreases and solar heating intensifies, mass loss should increase, perhaps steeply, if new volatile species begin sublimating. But predicting this curve requires knowing what ices are present, how deeply they're buried, and whether surface layers have been altered by cosmic ray exposure or prior heating events during previous close stellar encounters, if any. Comets do produce X-rays, but through a specific mechanism. When solar wind, a supersonic stream of charged particles flowing outward from the Sun, collides with neutral gas in a comet's coma, ions in the wind can capture electrons from the neutral molecules. This charge exchange process leaves the ion in an excited state, which then relaxes by emitting an X-ray photon. The phenomenon was first observed decades ago and is now well documented. Cometary X-ray emission is soft, peaking in the range of 0.3 to 0.8 kiloelectronvolts, correlates with solar wind density and velocity, and scales with the amount of neutral electronvolts, and scales with the amount of neutral gas available for interaction. Brighter, more active comets produce more X-rays, especially when solar wind conditions are enhanced during coronal mass ejections or high-speed streams. For 3I Atlas, the baseline prediction is straightforward. Given the inferred gas production rate, several kilograms per second, and typical solar wind conditions at 2 to 3 astronomical units, the expected X-ray luminosity should be detectable but faint, requiring several kiloseconds of integration time with integration time. Sensitive instruments. The emission should appear diffuse, spread across the coma, not sharply localized. It should vary with solar wind conditions, brightening when fast wind or transient structures sweep past, fading during quiet periods. It should also correlate with optical and ultraviolet tracers of gas production. When hydroxyl emission or co-lines strengthen, X-ray flux should rise proportionally, tracking the abundance of neutral targets available for charge exchange. The spectral shape should match theoretical models of highly ionized oxygen, carbon, and nitrogen capturing electrons, producing a characteristic pattern of emission lines that, though blended at moderate spectral resolution, collectively define the cometary X-ray signature. But the observed X-ray glow sits uneasily against this framework. The luminosity is not wildly excessive, but the variability pattern does not track optical gas proxies with expected fidelity. When hydroxyl emission increases sharply over 4 days, X-ray flux lags and rises by a smaller factor, as if the processes generating gas and X-rays are decoupled or responding to different drivers. The spatial distribution, though still diffuse, shows a persistent centroid offset, not large, but stable across multiple observations, implying that X-ray production might be concentrated toward one side of the coma, possibly tied to asymmetric outgassing or preferential solar wind interaction geometry. The energy spectrum fits a thermal plasma, which is not inherently wrong for charge exchange emission, but the residuals, small but systematic, hint that the emission might not be entirely charge exchange, or that the ion population in the solar wind is subtly unusual during these observations. Solar wind monitors show nothing extraordinary. The wind speed hovers near typical values, density fluctuates within normal ranges, and no major coronal mass ejections sweep past during the X-ray observation windows. If the glow were purely driven by charge exchange under standard conditions, the brightness should be lower, the variability tighter, and the spectral shape cleaner. Something about the interaction, either the gas composition, the geometry, the local plasma environment, or some process entirely separate from charge exchange, is not behaving as baseline models predict. Non-gravitational acceleration, the subtle force that nudges the object's trajectory slightly away from a purely gravitational path, shows up in the orbital residuals. Astrometry from multiple observatories, fitted with a model that includes solar gravity and perturbations from major planets, leaves systematic offsets that accumulate over weeks. These residuals can be reduced by adding a small acceleration term, typically aligned with the sun-to-object direction, as expected from outgassing-driven rocket thrust. For a typical comet, this acceleration scales predictably with gas production. More gas means more thrust, and the direction should align with the net outgassing vector, often pointing away from the sun with slight adjustments due to rotation and active region distribution. For 3I Atlas, the acceleration is present but odd. The magnitude is larger than gas production estimates suggest, by a factor of roughly 2, which could be explained if gas is escaping faster than inferred from brightness, or if mass loss estimates are too conservative. But the direction wanders. Some orbital fits prefer acceleration tilted by 15 degrees away from the expected anti-solar orientation, while others stabilize near radial but require episodic changes in thrust strength that don't correlate cleanly with observed brightness changes. Dust tail modeling compounds the puzzle. The tail, faint but detectable in deep images, should trace the trajectories of dust grains pushed by solar radiation pressure after ejection from the nucleus. The observed tail angle, however, doesn't quite match models assuming radial dust ejection and standard solar radiation pressure. It's off by several degrees, persistent across multiple epochs, implying either that dust is being ejected with an asymmetric velocity distribution, that radiation pressure is somehow modified, or that some other force is nudging dust grains slightly after ejection. Brightness irregularities add texture. The 8.3-hour periodicity seen in early data becomes less clean over time. Some nights, the light curve shows clear sinusoidal modulation, as expected if a rotating nucleus with asymmetric activity regions spins into and out of sunlight. Other nights, the periodicity fragments into multiple peaks or flattens into quasi-random flickering. Peak brightness shifts by 15% between observations separated by only a few days, faster than heliocentric distance changes can explain through solar heating alone. Spectroscopy reveals transient emission lines, brief flashes of hydroxyl or CN, that appear during optical brightenings but fade within hours, as if localized regions suddenly activate, then shut down. The X-ray glow weaves into this pattern inconsistently. During a 4-day brightening event where optical flux rises by 15%, X-ray counts increase only 8%, delayed by 18 hours. A second brightening episode 2 weeks later shows a similar delay, but the X-ray response is stronger, 12% flux increase, despite optical changes being nearly identical. The energy distribution of the X-rays shifts slightly. During bright phases, the spectrum hardens marginally, peaking closer to 0.7 kiloelectronvolts instead of 0.6, then softening again as optical brightness fades. This behavior is not random. It's structured, repeatable in gross features, if not in precise numbers. But it resists the simple correlations that charge exchange models predict. If solar wind were the sole driver, X-rays should track gas production tightly, fluctuating in lockstep with hydroxyl or co-emission. Instead, they flicker with partial correlation, as if responding to gas production and something else. Perhaps solar wind microstructure, perhaps geometry changes, perhaps an additional energy source intermittently active. Each contradiction, examined alone, has plausible outs. Non-gravitational acceleration could be larger if outgassing is underestimated. Tail angles could be off if dust grains are unusually porous or electrically charged. Brightness variability could be chaotic if the nucleus is fragmenting slowly, exposing fresh ice intermittently. X-ray delays could result from time-varying solar wind speed, where fast wind takes time to propagate from sun to comet, decoupling gas production from X-ray generation by propagation lag. But these explanations, stacked together, begin to feel strained. The object resists fitting cleanly into a single coherent model, where all observations align under shared physics. The conservative approach begins with instrumental and geometric artifacts. Could the X-ray detection be a background source, a faint galaxy or distant quasar, coincidentally aligned with the object's trajectory? Probability analysis says no. The sky density of X-ray sources at this flux level is low enough that chance alignment over multiple epochs, each matching the object's motion, is vanishingly improbable. Could ephemeris errors place the object slightly off its true position, causing the X-ray centroid offset? Astrometry from Gaia and optical follow-ups pins the object's position to within a few tenths of an arcsecond, far tighter than the 2 arcsecond X-ray offset, ruling out ephemeris as the culprit. Could detector gain drift or calibration errors create false spectral features? Cross-checks with celestial calibration sources observed during the same orbital period show no systematic offsets, and spectral residuals persist across independent reprocessing pipelines. Within standard physics, solar wind charge exchange remains the leading candidate, but it must be tailored. Perhaps 3A. Atlas is unusually rich in carbon monoxide or carbon dioxide, gases that sublimate at lower temperatures than water, allowing significant neutral gas production even at several astronomical units from the Sun, where water-dominated comets remain mostly dormant. Enhanced KIO production would provide abundant charge exchange targets without proportionally increasing optical brightness, since KO doesn't scatter sunlight efficiently. This could explain why X-rays appear stronger than optical gas proxies suggest. Spectroscopic searches for CO have been ambiguous, tentative detections, but noisy, leaving this hypothesis plausible but not confirmed. Solar wind conditions, while not extraordinary globally, might vary locally. The heliospheric magnetic field drapes around obstacles, and density or velocity enhancements on scales smaller than spacecraft could create pockets of intense interaction. If 3 ILS happened to be passing through a region where solar wind speed increased by 20% over a few hours, charge exchange rates would spike, producing an X-ray brightening decoupled from the object's intrinsic gas production. Testing this requires solar wind monitors close to the object's position in space, data rarely available unless spacecraft happen to be nearby, making the hypothesis difficult to falsify directly. Phase-changing ices offer another avenue. If the nucleus contains exotic volatiles, ammonia, methane, nitrogen, or amorphous water ice, transitioning to crystalline structure, sublimation rates might change abruptly at specific temperatures, triggering sudden outbursts that don't scale smoothly with heliocentric distance. These transitions could also release trapped gases suddenly, creating transient enhancements in coma density that last hours to days before dissipating. Such behavior could explain episodic brightenings and non-gravitational acceleration variations, though linking this to X-rays still requires invoking charge exchange with transiently enhanced gas production. Dust physics becomes more speculative but scientifically grounded. If dust grains are fractal aggregates, loosely bound clusters of tiny particles with large surface area, they interact with sunlight differently than compact spheres. Radiation pressure scales with cross-sectional area, but mass scales with volume, so fractal grains experience stronger pushes, potentially explaining anomalous tail geometry. Thermal emission from fractal dust might also be subtly different, affecting albedo and size estimates. If grains are electrically charged, possible if photoelectron emission or plasma interactions charge the surface, they could respond to the interplanetary magnetic field, adding a small non-gravitational force perpendicular to the sun direction. Such forces are weak, but over weeks could produce measurable trajectory deviations or dust tail distortions. Swarm-like structure, a distributed cloud of fragments rather than a single nucleus, enters the discussion cautiously. If the object consists of many smaller bodies orbiting each other loosely, or debris from a recent breakup event, brightness variability becomes easier to explain. Different pieces rotate with different periods, active regions turn on and off independently, and the collective light curve is a sum of asynchronous contributors producing irregular flickering. The X-ray glow could be distributed across the swarm, with different fragments interacting with solar wind independently, creating a diffuse emission region that appears as a single source when observed at limited spatial resolution. This model does not invoke intelligence or intention. It is purely gravitational and thermal fragmentation, similar to shattered asteroids or tidally disrupted comets, but it complicates interpretation because the object becomes a population, not an individual. At the boundary of conventional explanation, propulsion-like acceleration signatures warrant mention, not as assertion but as phenomenological description. If an object exhibits non-gravitational force that does not correlate with observed outgassing, persists asymmetrically, and adjusts direction over time, it resembles thrust. Natural processes, asymmetric outgassing from rotating vents, preferential sublimation from sun-facing cliffs, can produce thrust without invoking technology. But if the acceleration vector changes faster than rotation can explain, or if thrust appears during periods when gas production is minimal, the phenomenology starts to strain natural model. Evidence required to move this from interesting pattern to extraordinary claim is stringent. High-cadence photometry showing thrust correlating with brightness in ways inconsistent with sublimation thermodynamics, spectroscopy confirming gas composition and flow directions, or spatial imaging resolving asymmetric features incompatible with passive thermal response. None of this evidence yet exists at the necessary quality. The discriminators, measurements that could separate these hypotheses, are clear. Simultaneous X-ray and ultraviolet observations would test charge exchange directly. Hydroxyl emission traces water dissociation products, and if X-rays track hydroxyl brightness with appropriate time lag for solar wind propagation, charge exchange is confirmed. If they don't, alternative mechanisms gain weight. High-resolution mid-infrared imaging could resolve the nucleus or detect multiple fragments, settling the swarm question. Rotation phase resolved spectroscopy would reveal whether gas emission turns on and off with specific viewing angles, indicating localized vents, or remains steady, suggesting distributed activity. Radio observations of carbon monoxide, with velocity-resolved profiles, could map gas flow geometry, testing whether outgassing is radial or asymmetric. Monitoring X-ray flux during known solar wind transients, when spacecraft near Earth detect coronal mass ejections or high-speed streams, would confirm whether the glow responds to external drivers or persists independently. The orbit arcs forward, carrying 3I Atlas deeper into the inner solar system over the coming months, then outward again toward interstellar departure. Heliocentric distance will decrease to roughly 1.8 astronomical units before reversing, a modest perihelion that won't subject the object to intense heating, but should still increase sublimation rates noticeably. Observational geometry improves for several weeks, then degrades as Earth's motion carries us away from favorable viewing angles. Ground-based telescopes will have brief windows of optimal positioning, then the object will sink into twilight as seen from Earth's night side, accessible only to space telescopes unburdened by daylight. Jupiter's gravity lies along the outbound trajectory, not as a close encounter but as a distant perturbation, bending the path slightly without dramatically altering the hyperbolic excess velocity. Small trajectory changes matter for scheduling. Shifts of a few arcseconds affect which telescopes can coordinate simultaneous observations, and for interpreting future astrometry, since even tiny unmodeled forces accumulate into detectable residuals over months. If non-gravitational acceleration continues, the outbound trajectory will deviate measurably from purely gravitational predictions, providing a test. Does the thrust persist, grow, or shut off as solar heating wanes? Light curve forecasts depend on assumed physics. If the 8.3-hour periodicity reflects rotation, it should persist, possibly evolving slowly if outgassing torques spin the nucleus up or down. If it reflects structural resonance or fragment orbits, it might drift or break apart entirely if the object is disintegrating. If X-rays trace charge exchange, brightness should peak near perihelion when gas production maximizes, then fade as the object recedes and sublimates less vigorously. If X-rays depend on exotic ices transitioning at specific temperatures, brightness might spike abruptly when thermal thresholds are crossed, then plateau or drop discontinuously. If fragmentation dominates, variability could become stochastic, less predictable in detail but statistically characterizable, showing increasing scatter as pieces separate and evolve independently. Coordinated campaigns are being planned. Optical spectroscopy from multiple sites will track hydroxyl, CN, and C2 emission across rotation phases, building maps of gas production versus viewing angle. Infrared imaging will monitor thermal emission, constraining albedo and testing whether surface temperature distributions are consistent with a single rotating body or multiple fragments. ALMA will observe carbon monoxide at high spectral resolution, mapping velocity fields to reconstruct three-dimensional gas flow. X-ray observatories will revisit the target with longer exposures and tighter cadence, coordinating with solar wind spacecraft to catch correlation or lack thereof. Ground-based photometry networks will maintain nightly coverage, capturing transient events that could be missed by infrequent snapshots. The next data will not solve the mystery cleanly. It will instead collapse the hypothesis space, ruling out explanations that predict behaviors not seen, elevating those whose predictions match. If X-rays fade as solar wind quiets, charge exchange strengthens. If they persist during solar wind lulls, something else matters. If hydroxyl and X-rays suddenly lock in phase, the delay was propagation lag. If they never correlate, the glow is decoupled from water-driven outgassing. Each observation adds a constraint, narrowing the range of viable models until only one, or perhaps none, fits comfortably. The glow remains as the object drifts through the dark, tumbling slowly, shedding gas and dust molecule by molecule into the solar wind's invisible flow. Instruments watch, photon by photon, building statistics that will eventually speak with confidence or ambiguity, but speak nonetheless. The universe has always offered phenomena that violate first expectations. Quasars were once mysterious. Pulsars seemed impossible. Fast radio bursts defied models for years before coherent explanations emerged. This X-ray glow, faint and flickering, sits in that lineage, not proof of the extraordinary, but a reminder that our models are approximations, our intuitions incomplete, and our instruments capable of seeing things we did not predict. Science proceeds not by demanding immediate answers, but by sharpening questions. What gas composition would produce this X-ray spectrum under standard charge exchange? If not standard, what ion population or interaction geometry? What thermal evolution explains episodic brightness changes? If fragmentation, when did it occur, and what triggered it? If exotic ices, which molecules, and at what depths? The mystery is not failure, it is the engine. It drives observation schedules, motivates new instrument proposals, and forces theorists to explore edge cases in physics long assumed settled. The object will leave. Eventually, gravity and velocity will carry it beyond the heliopause, back into interstellar space, where solar wind fades and sunlight becomes just another star. Telescopes will track it as long as brightness permits, until it becomes too faint, too distant, too slow-moving to separate from background stars. The data will remain archived, public, waiting for future analysts with better models or new ideas. Perhaps someone will notice a pattern missed now. Perhaps comparison with the next interstellar visitor will reveal commonalities or stark differences. Perhaps the X-ray glow will be retrospectively understood as something mundane, a corner case of known physics, finally properly modeled. Or perhaps it will remain a footnote, a curiosity that hinted at processes we still don't fully grasp. We stand at the edge of what we know. Instruments pointed upward, watching light that left the object minutes ago, carrying information encoded in wavelength and arrival time. The glow asks no questions, it simply is. We are the ones asking, testing, doubting, and wondering. The patience required is not the universe's. It is ours.